Record. Okay, so now I'm recording again. Yeah, so this is the lab 2 part then. So going back a bit, you're going to investigate how well your amplifier behaves in this accumulator structure. So this is the parasitic sensitive version that I'm drawing here. It's sensitive towards parasitics because if I introduce a parasitic capacitance in any of all these nodes, which ones will influence my transfer function? So for example, if I had a parasitic capacitance down here, so with every single node, we can associate the parasitic. So either it's associated with the plates of the capacitor or the switch or the Mos transistor input or the Mos transistor output. I mean, after all, you have a pole here, which is dictated by an output impedance and a capacitance. So if I introduce these parasitics in all my nodes, in all possible cases or places rather, you know, plenty of these guys, you can quite easily see that the guys that are shorted all the time between potentials or nodes of same potential, they don't influence the result because they are always shorted. So this guy doesn't matter. This guy doesn't matter. That guy doesn't matter because it's virtual ground and ground. This one doesn't matter either because the input voltage acts like an ideal voltage source. So whatever I connect in parallel here doesn't make sense. Or well, it makes sense to some degree, but it doesn't influence the voltage because it's in parallel with an ideal voltage source. This guy, for the same argument, if we treat the op-amp as an ideal component, it's going also to act like an output, like a voltage source here. So this capacitor and obviously that capacitor is in parallel here with the voltage source. So that's also going to be quite easily removed from the equations. The output voltage is dictating the voltage here, regardless of the capacitors. And this guy also is in parallel with that capacitor. So that one is also connected between virtual ground and real ground. So they're always shorted. However, that guy is the problem. It's connected in parallel with C1. So the effective parasitic here is C1 plus this small parasitic down here. So one exercise was to demonstrate this and show what could be an insensitive architecture, the ones that you are using in the filter. Because then you have capacitors which are always connected to or between ground and virtual grounds, etc. So a bit messy, but you know the strategy is quite straightforward, and you also have help material in the PDFs on the LISAM to assist you there. All right, so op-amp, going back, lab 1. You noticed already that there were some issues designing the amplifier with proper gain. And there is a certain reason for that, quite obvious reason, to be honest. If we go back to our op-amp, if we sort of zoom in here, if you just take this architecture, which has been provided to you without any modifications, you're quite free to do modifications, of course. There is nothing per se dictated that you should use this amplifier, but yeah. Okay, so this is the equivalent model. So essentially a current source down here, which is a Mos transistor, and your input stage here, like this, and then you have a transistor pair, a current mirror on top here. So I'm just sketching the output stage, or these two stages of your amplifier, the equivalent model. So we can ignore the tail current source down here because the way the differential signal is applied to these two transistors is that they cancel each other. So this node down here is AC-wise grounded. And then it sees this load, the current primary side of this current mirror, and then the secondary side multiplies the current with a factor K and brings it to the load, the active load, the current source down here, and then we have the output voltage. So if we look at the transfer function, which you derived probably last time for your exercise, it's quite easily given by GM1. And here we have GM, now I just invent the number, GM2. And this guy multiplies by a factor K. So this guy is K times GM2. Then we have a certain load here, output impedance or admittance, which is GP plus GN here. Okay, so the total gain is GM1 divided by GM2 times K GM2 divided by GP plus GN. All right, so GM2 cancels each other. And then you have K times GM1 divided by this factor. And if you remember, I mentioned early in the lectures that this ratio is not very big for a modern transistor, a factor 6 or 7 or something like that. This channel length modulation is big for a small geometry transistor, and these guys are in 40 nanometers. So either you have to increase the channel length to make this factor bigger, or you have to increase the K to make the gain higher, one would guess. But if you look at the equations, what happens here, remember that we have an expression for GM1 and these guys. Let's bring that here. We know that GM1 was equal to, GM1 was equal to 2 times the current divided by V effective. So that's my ratio for this input transistor, and the V effective is given by my voltage specification in. And what else do we know? We know that GP plus GN was equal to some sort of lambda average times 2 times the current, this branch, this branch. So whatever current I have here dictates my output admittance according to that formula, lambda I. And what do we know about this current on the output stage? Well, we know it's that current, I naught times K. So if we combine these two equations, the expression for the gain, so K times GM1 divided by GP plus GN, that's equal to K times 2I naught divided by VF, this guy, divided by 2 average lambda I naught times K. And then you see something interesting, that the I naughts cancel, but also does the K. So whatever we have and the 2 disappear. So the only thing we have left is lambda average VF. So it's independent on the factor K. So some of you have already probably discovered this to some extent. There are, of course, secondary effects associated with this. This VF might change slightly and things like this. So you probably see a weaker relationship or function of K. So maybe you see something like A is maybe, something like square root of K, or even weaker function than that. So in order to address this, a key target is obviously try to make L channel length as high as possible or long as possible. And the drawback with that is what you probably have already discovered, that if you make the channel lengths larger, these guys will be bigger, and they will thus also have higher capacitance, the parasitic capacitance we find here, which is the CGS, the gate source capacitance of these 1 plus K unit transistors. So whatever you try to do in order to increase the gain will penalize your bandwidth, or at least phase margin, as you mentioned. The capacitive load is already there. All right, so essentially you have 2, 3, 4 issues to deal with when you replace the ideal operational amplifier with your implementation. Gain is one of them. So we have to investigate today in my sort of first 30 minutes here. We will do an analysis of the op-amp with respect to limited gain. Because the gain you have, if you haven't done any changes to your op-amp, which you are free to do, but if you just take the vanilla or the given architecture or topology, the A0 is limited to 30 dBs, and that's not much. That's less than 100, so it's a very low amp gain though. So what's the impact on the Switcap circuit in that case? And then also bandwidth. So you might have some bandwidth issues. Now you have a pretty fast device, 500 megahertz, so you're less dependent on that. But remember that the bandwidth of the operational amplifier has to deal with the bandwidth or the clock frequency of the switching activity. So even though your signal is operating at the low frequency, you have to remember that F sample is much, much higher than F signal. And your operational amplifier has to cope with that frequency. And you have to make sure that the bandwidth of your system, bandwidth, which is equal to beta times the unity gain frequency of your op-amp, has to be larger than the sample frequency to some extent. Otherwise, the system will be too slow and not be able to. Essentially, I mean, you have your clock phases like this that control a switch, which the op-amp might drive, and it should charge the capacitor. So obviously, you're charging the cap during the time t half, if this is your time period, t. So you charge the capacitor during t half time, this period, for example. And obviously, if you have a pole here, a system with a certain bandwidth, it will be behaving like if it's a dominant pole, it will behave like a first order RC, what do you call it, charge or discharging curve. You will get something like e to the minus t divided by RC, where this is the pole of your system, beta omega UG, like this. So if I have a step pulse happening here, I have the ambition to charge my capacitor really fast, but in reality, I will have a delay due to my op-amp being too slow. So it will sort of behave something like this. Charging curve that we recognize from the basic courses, e to the e minus t, and time constant of the system is given by the pole of my operational amplifier. So you obviously see then that this beta omega UG has to be faster than half the clock or sample period when we start switching the switches back and forth here. Okay, so bandwidth is definitely an issue and limited gain. And then, well, there are plenty of others. So sorry, a little bit messy here, but let's borrow some space or just pick another. So the next option is the voltage swing. So that's another limitation. If you look at your op-amp, so let's spend a minute here. So it looks something like this. And then you have your input here somewhere and your output. Something like this. So the input voltage, we recognize from the preparatory questions that it has to have a voltage swing which is higher than these two jumps. So first of all, we need one VT here to start this transistor. And we also need some margin in order to bring this safely into the saturation region. And we also need to provide this guy, the transistor down here, with a certain margin. So I definitely need V in to be larger than VT plus 2 delta Vs. So this is one of the issues you have in the first lab, that the common mode range, the range over which I can sweep my input voltage, is quite aggressively specified in the table. You definitely need to be above VT. So are the 0.25 volts in the specification sheet really appropriate? And there is also a limit from above. We know that we have here, in order to turn this guy on, we need a VT, a threshold voltage, because they are connected here, and some margin. So we have VT plus delta V here. And this guy is delta V. And this guy up here is VT plus delta V. So VT plus margin, delta V, and VDD up here. So I can also define an upper bound on my input voltage too, because I see that VDD minus VT plus delta V minus delta V plus delta V plus VT has a certain impact also on my input voltage. So if I do my jumps here up to VDD and go down this path and up to V in again, that gives me an upper bound of V in. So in this particular case, it's quite kind to us, because the VTs will cancel each other. This guy will disappear. These two will disappear. So in this particular case, it's doable with a pretty high voltage in this case. But there could be other issues limiting my input voltage. And output voltage is the same story here. We need some delta V margin here and delta V margin here to keep these transistors in the saturation region such that they do have gain, which means that on the output voltage you are sort of bound by delta V less than V out less than VDD minus delta V, delta V. So say 100 millivolts up to 0.9 volts or something like that. So just a very quick idea on, this is explained also in the material, but keep track of what the specification says if this is really doable. Probably fine in the upper end here for V in, and probably okay for V out, but probably not okay for the lower end. So in your case, when you start hooking up the system, are you really able to handle the voltage swings that you apply to the op-amp? So it's probably okay to some extent on the input, because that's locked due to the operation of the gain of the amplifier and the virtual ground here. So this voltage is probably fine. However, this output voltage of my op-amp, you have to think of, am I overdriving the output such that I get a really nonlinear behavior and gain is lost in the feedback, etc. So voltage swing is also very important to understand. And then the last one, so switch on resistance. Switch on resistance. Okay, so we might do some calculations on this soon. We'll see how much time we need to spend on that. But we do have a system you know, like this, and my op amp, V in, V out. And then you have here a MOS transistor defining the switch. So this will typically be looking something like this. So switch signal phi, for example, and phi inverse here. And these will also be non-overlapping phases. It's really important. So we typically have phi maybe being like this. So that's phi. And then we need to design them to be non-overlapping. So phi bar will look something like this instead. So phi bar. And why do they have to be non-overlapping? Well, that's if they would be overlapping, there would be a short between V in and this virtual ground for a short period of time. And that's enough to ruin the whole system. So non-overlapping phases is a key thing. That's been prepared to you. You find a certain cell for that in your lab. So you have phi 1 and phi 2 or phi bar already given for you. But just in case you wonder why it's there, it's a specific reason. These guys are associated with the resistance. If they are MOS transistors, the resistance of a MOS transistor is in the order of 1 over alpha VDS minus VT, roughly, give or take. Which means that you have some resistance, and this behavior is pretty similar to whatever we discussed about the bandwidth here. So if we have a system which has to charge something, there will be a resistance also in the switch, and that will give us this e to the minus blah, blah, blah. So that's sort of similar operation. So you have to also investigate here because that gives you a requirement on the switch, the resistance and the size of this transistor that you implement the switch with. And one could argue, okay, the pretty relaxed requirements actually. You will find that in your simulations, but you have to remember that you are supposed to settle to a certain accuracy. So we can't only, if this is R on here, and this is my C, I obviously have something like a time constant R on times C this way. But if you remember from school, if this is equal to half the clock period, we only reach roughly 70% of the end value. And we might have a system here which needs, say, an accuracy of 0.01% or something. So this one has to settle within 0.01% of my target end result. So if I have my square wave coming in and I expect some settling like this on the output due to the resistance, well, then the settling error, once I close the switch again at t-half, this error has to follow the same accuracy as the whole system. So if this would be a data converter, for example, with say 10 bits of accuracy, this one has to settle within 0.1%, 1 over 1024 accuracy. So once we start to add these sort of strict requirements on accuracy, then this R on has to be pretty low after all. Not super low, but you can't just ignore it. All right, so I sort of motivated. So you who have struggled with finding gain, there is a reason why it's difficult. There are ways to mitigate it. Either you make a topological change, or you play around with the channel length of the transistors. Okay, they went here. Yeah. So either you play around with the channel length of the transistor, and try to handle the phase margin because you introduce a second pole. That you can do with some compensation tricks with lead lag, etc. But it might be a little bit out of the scope to try to really push the limits, but it's a good practice in order to understand that further. All right, so I'll spend some more minutes and then I'll let you continue work on your own. So if you go to Lisan, the Lisan folders, so let's maximize this a bit. And that didn't help super much. Anyway, you have some PDFs lying around there. There's one called Non-Ideal Switcap Slides, which you can look into. And as I mentioned also in the Teams channel, you have lots of stuff in the Lisan folders with a lot of descriptions of filters and filter design and Switcap filter design. So go through all these, well, not all of them perhaps, but look through them and scan for what you need for your project. So let's just quickly look at this slide. So here you have the document 45 non-ideal SC slides. Something like that. So it explains impact of offset error if you have mismatch in your design, which you don't do in this lab series. So this is, but it explains how you can think. Gain error, so I think we should probably look into this today. Just to talk a little bit about that. And then we have this bandwidth discussion that I said, rise and fall times due to the charging, blah, blah, blah. And then you can look at some conclusions from that. Slew rate is, you have to make sure you don't limit the current drive capability for your device. So there was a slew rate requirement in the spec. Let's see, make it a little bit bigger. Yeah. So you have a maximum current that you can pull, which is essentially given by the power consumption in your device. So that current has to be able to drive or charge C2 within half a clock period. So that's what you have to be thinking of. So first of all, you have C2, which it might have to charge, and also some additional load on the output here. So that's something you have to consider when you design your filter. How much capacitive load do I drive? And is that sufficiently small such that my output current can charge the voltage or the capacitor to a certain voltage within half my clock period, tau. That's super hard to do calculations on because it's so nonlinear, so there's not much we can add there. Noise you don't do in this course, but there are some information on that. On resistance, I discussed, same thing here. You have some rise and fall times, and you can look at the quite clever way of writing this as a charge rather than voltage, and then you get the relationship or a difference equation with respect to the charge rather than voltage, and then we can formulate an equation which gives us a certain interesting behavior here, which I urge you to look into. We have the ideal transfer function, and then we have some additional terms here which you can look for in your simulations then later down the road, etc., and some more. But in your task is to investigate the behavior as a function of bandwidth, gain, and on resistance of your switch. So I suggest that we spend a couple of minutes just to refresh charge sharing, etc., and look at let's look at gain errors. I think that's good enough for now. So I'm just going to outline the reasoning behind these calculations, and then I'm going to stop talk for an hour and have your questions coming up instead. So Let's get rid of that one. Something like this. All right, so the question is, we do have an accumulator, and in this particular case, I'm going to use my non-parasitic or parasitic insensitive, sorry, version of my accumulator. And it looks something like this. Minus and plus, and ground. V1 and V2. All right. So it has two switches, which we can flip back and forth a bit to change the sign and delay through our circuit. We have a C2 and we have a C1. And then I mentioned the reference directions. So in my case, I typically choose my reference direction towards the charging nodes like V1 and V2. And these guys are only there in order to help you do the charge redistribution analysis. They're not saying anything about the direction or polarity of the capacitor. It's just a pure aid for your eye in order to keep track of things in your analysis. All right. Okay, so normal charge redistribution is also in the material, so you can take a look at that. And we also did some of this on the lecture, 2 lectures ago. So what happens if you have limited gain in this guy? So in our simple model, we assume that V2 is equal to Vx times A. So I have a limited A, which is not infinite. And that in turn is going to make the following. I'll take the Vx, this is this voltage here, from plus to minus. So that's 0 minus, let's call this node VA. So minus VA times A, which obviously makes VA equal to V2 divided by A. Okay, and a minus. Something like that. Right, so here you have to be a bit careful then. The statement I made before about voltage swing. So if this guy swings 0 to 1 volt, for example, and then you have a limited gain in your device, which in your case is less than 100. So, you know, this voltage is going to swing quite a lot. So in your case, VA is going to be in the order of 1 volt divided by 30 decibels, which is like 40 times or something. So 25 millivolts. So this is going to switch quite much. Okay, so from a charge analysis point of view then, we can do the following. So what we do during the analysis, we note down the charges during the 2 clock phases or 3 phases, and then we look at the distribution of charge between the different phases. So at phi 1, and in this case, I'm going to toggle these ones. I'm going to say that the red here, that's my phi 1, and the blue one is phi 2. So in the first phase, we assume we charge C1 just for simplicity of the analysis. So now we can just say that Q1 of N, that's going to be equal to V1 of N minus plus, because we know that voltage is going to be V2 now. V2 of N divided by A, like that, times the capacitance C1. So that's just noted. And then we do the same thing for Q2 or C2. So we have Q2 of N, and notice my reference direction. So I'm going to sort of calculate from the V2 direction. V2 of N plus V2 of N divided by A, C2. So if this would be the original case with infinite gain, I wouldn't see that guy. Well, I wouldn't see any of those two. But now we see there is something happening here to the transfer function. There is a sort of dependency. Also during the charging of C1 during the first phase, we are dependent on the output. All right, then we do the switching infinitely fast without overlapping clock cycles. So at phi 2, so Q1, nothing interesting, it's 0. So we charge C1 between ground and ground. So Q1 of n plus a half is equal to 0. And then Q2, so this is disconnected, and we simply get Q2 of n plus a half is equal to, well, same expression really, V2 of n plus a half plus V2 of n plus a half divided by a times C2 also. So I should times C2. All right. So not really rocket science, it's just these guys coming up. So that's the first step of the analysis. Normally we would also do this step in the third phase analysis, but we're pretty certain that this will be same, but will just be n plus 1, n plus 1, n plus 1 everywhere. So let's look at some charge redistribution or preservation. So that's going to happen in two phases, so either from phi 1 to phi 2. Let's look at what's happening. Phi 1 to phi 2, so the first step. So what's happening is that we're going to switch this away from this virtual node, from red phi 1 to blue phi 2. And then the preservation will only be given by C2, more or less. So the charge on C2 is maintained. So we do have that Q1 is obviously flushed, so that doesn't make sense to analyze. And then we have simply Q1 of n plus a half is thus equal to Q2 of n. So the charge is simply preserved on C2, this plate. I infinitely fast remove the switch here. Okay, and then, yeah, since the expression here are identical, we can just simply say that these two are equal to each other then. So that directly implies that V2 of n plus a half is equal to V2 of n. That's what we can conclude. And then we look at the next transition from phi 2 to phi 1. So we switch from blue to red. So now we're going to charge C1 to the virtual ground, but nasty probably, or whatever sign we have here, would probably steal from C2. So we have a preservation of the total charge from these two negative plates of the capacitors. All right, so that gives us that minus Q1 of n plus 1 plus minus Q2 of n plus 1 in the new phi 1 phase, the third phase. That's going to be equal to minus Q1 of n plus a half minus Q2 of n plus a half. And that we already know is 0. That's going to be 0. This guy we already know from up here that that's going to be equal to Q2 of n, or minus. So the difference equation is quite simple. We have Q1 n plus 1 something something like this. Do we need to yeah, so we will just simply move everything here and so how much do I want to write here? Essentially, I want to take this whole expression v1 blah 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 into this expression equal to this whole expression with 2 time indices. So that's probably going to be a bit time consuming. We will find only a v1 expression from this guy, and then we will find a couple of v2 expressions from that guy. So I would have something like c1 of v1 of n equals to something blah 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 v2 of n plus something blah 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 v2 of n plus 1, something like this. If I combine the two equations, I'm not going to do that here because it's pretty straightforward. It's just ink, and instead we get to the final expression. So that implies that we use Z transform, a discrete time Laplace transform, because it's a difference equation. And we find the solution that V2 divided by V1 of Z, that's going to be equal to C1 divided by C2, 1 plus 1 over A naught. Now I'm reading directly from the PDF here just to save us some time. So 1 plus yeah, so pretty large expression after all, and especially I would like to save us some time to do the calculations there. Anyway, what we can conclude here, if we compare with the original, C1 divided by C2, 1 minus Z minus 1, or something like that, Z minus 1. We do have two phenomena. So first of all, you have this guy giving you a gain error. And then, perhaps more importantly, you also have something which is not 1 here in the numerator, in the denominator, sorry. You have a pole which has moved away from the unit circle. So if you look at this expression, that's a discrete time pole here on the unit circle. But in this case, it's moving inside a bit. So I have my unit circle and the pole has moved inside the circle a little bit, not much, but a little bit. That implies that you have something called a lossy integrator. Or accumulator. And that in turn implies something. If you do the end value theorem in a discrete time world, and I would like to investigate when Z is equal to 1 for the end value theorem, you can see that this expression goes to A naught. So let's just conclude before we take a break. So end value theorem. Right, so I've done my big calculation here. Concluded on this expression, so take a look in the PDF. Will help you. Gain error, a slight pole change here, and then I can investigate the end value by setting Z equal to 1 and take the limes of that. In this particular case, there is nothing interesting with the limes, but Z, etc. here will disappear, and I will get an expression which says that V2 of 1 divided by V1 of 1 goes to A naught. So that's pretty interesting because that tells you that your amplifier cannot accumulate a voltage more than A naught times. So if you would take a a real accumulator, which will be ideal. You would have 0 from and put the DC voltage at the input, for example. It will accumulate, you know, forever, etc. But in your case, since you have limited gain of your amplifier, it will saturate to A0 times 10. So it will try to accumulate well here, but after a while it will just die and cannot accumulate more than that. So that's a quite important effect that you have to watch out for. All right, so I've been talking a little bit too much, maybe, but the purpose of these hours are for